Hello everyone, this is part 6 video on past year NEET questions from the topic electrostatics and capacitors. Those who are looking at the video can also take a look at the previous video so that you will have continuity of questions. We'll start with a question that has come in the 2005. This is a question based on the combination of capacitors. A network of 4 capacitors, they are giving us the values. C1 is equal to C, C2 is equal to 2C, so this is C, this is 2C, and C3 is equal to 3C, and C4 is equal to 4C, are connected to a battery as shown in the figure. So the voltage of the battery is V. The ratio of charges on C2 to C4 means we need to find what is the ratio of charge on C2 to C4. So if you call the charge on C2 as, say, for example, Q2, and charge on the C4 as Q4, then they're asking us what is this Q2 by Q4 ratio. So how are we going to proceed with this? If you look at it, right, the C1, C2 and C3, they are in a series combination, and that entire branch is in parallel with C4, which is of course in parallel with the battery. So first thing is we can easily find out what is the charge on the capacitor 4. Why? Because this is in parallel with the battery, right? Battery voltage is V, means the potential difference across the capacitor plates will be what? V. So charge will be equal to what? Capacitance, which is 4C into V. So straight away we are able to get it. Now how are we going to find the charge on the C2? If you look at the branch where the C3, C2, C1 are present, we will try to find out what is the equivalent capacitance, because if you replace them with an equivalent capacitance, right, whatever the charge on the equivalent capacitance, C1, C2, C3, they are in series, means all of them will be having the same charge. C1, C2, C3, they are in series, right, means what? They will have the same charge, and the charge will be equal to charge on the equivalent capacitance. So here look at it, C3 is what? This is 3C, this is 2C, this is C. We have to find the equivalent. They are in series, right? Means what? 1 by C equivalent is equal to 1 by C plus 1 by 2C plus 1 by 3C. What is the LCM of the denominators? It is 6C. So we will get a 6 plus 3 plus 2. Totally it will be 11 by 6C. That is 1 by C equivalent. Means C equivalent will be equal to what? 6C by 11. This equivalent, right, the C equivalent along with the C4, this is C4, will be in parallel arrangement with the battery. So charge on the C equivalent will be what? Charge on C equivalent will be its capacitance into the potential difference across it. Now this will be the charge on the capacitor 2 also, which will be of course charge on the capacitor 1 and also capacitor 3, because all these three are in series arrangement. So this is our Q2 value. Now they are asking us what? Q2 by Q4 ratio, right? Now we will just erase some part of it so that we will be able to. So now we have got the values, we just have to take the ratio, that's it. So we have the Q2, we have the Q4, we'll just have to take the ratio of both of them. So we have to do what? Q2 by Q4. So what is Q2 by Q4 going to be? Q2 is this one, right? 6C by 11 into V divided by 4C into V. So V is cancelled, CC also will be cancelled. We'll have 6 by 44. That will be equal to what? 3 by 22. 6 by 44, that will be equal to 3 by 22. So this will be the ratio of charge on C2 to the C4. Correct answer is option B. So what are we doing essentially here? We are looking at the equivalent capacitance of that combination, and whatever is the charge on that equivalent capacitance, right, same will be charge on all these three which are in series, C1, C2, C3. That's how we are able to get the charge on the capacitor plate 2. We'll go to the next question. This one has come in 2005. As per the diagram, point charge plus Q is placed at the origin. So at the origin we are keeping a point charge plus q. Work done in taking another charge minus q from point A is here, coordinates are 0 comma a, it is on the y-axis. We are taking a minus q charge from point A to another point B. Point B is on the x-axis along the straight path A to B. So we are taking the minus q charge along the straight path A to B. Now when we talk about the work done, right, so what will be the work done in moving this minus q charge? Minus q is the charge we are moving into potential difference between the 2 points, which is what? We are moving from A to B, right? So it will be what? Potential at the final location, which is VB minus VA. How is this potential coming? It is coming because of the charge at the origin. So because of the charge at the origin, right, what is the distance to the point A? It is A, because point A is having the coordinate 0 comma A, right, which means the y coordinate value is A, so distance is A. So VA will be equal to K into Q by A. Similarly, what about VB? Point B is again at a distance A, because here we have to look at the x coordinate, right? Point B x coordinate is what? A. So the distance from origin to point B is A only. So again the potential here because of the charge at the origin is what? Same, KQ by A, which means what? VB is equal to VA. So delta V will be what? 0. Since delta V is 0, the amount of work to be done in moving the minus q charge from A to B will be equal to what? 0. So the correct answer for this is what? The work to be done will be equal to what? It will be 0. Correct answer is option A. Next we have a question that has come in the year 2005. Two charges Q1 and Q2 are placed 30 centimeters apart. So you can see the charge Q1 is placed at point A and Q2 is placed at point B. A third charge Q3 is moved along the arc of a circle of radius 40 centimeters from C to D. Means initially it is at point C. We are moving it along the circular arc. So means AD will be equal to what? Same 40 centimeters. Means BD will be 10 centimeter. The change in potential energy of the system is Q by 3 4 pi epsilon naught into K. So here we have to tell what is the value of this K. So what do you mean by the change in potential energy? So if you look at the initial arrangement, right, Q3 is here, Q1 is here, and then Q2 is here. It's a combination of three charges. This is 40 centimeters, this is 30 centimeter. So this is a right angle triangle, right? This is a right angle triangle. So the hypotenuse will be what? It will be 50 centimeters. Height is 40 and base is 30, means hypotenuse will be what? Root of base square plus height square, that will be 50 centimeters. Now the three charges will have three potential energy terms. Initially this is the arrangement. We have A here, this is B, and this is C. Three potential energy terms will be there. Potential energy for the charge Q1 and Q2, AB, plus potential energy for the charges Q1 and Q3, plus potential energy for the charge Q3 and Q2. So here these the distances, right, they are in terms of centimeters. If we convert this into meter, means what? This will be 0.4 meter, this will be 0.5 meters, this will be 0.3 meters. Now we'll just write down the expression. The initial potential energy of the system. System means we have three pairs of charges. There will be three potential energy terms. What is it going to be? We will probably write this at the top and keep it. So we will have to write down what is the initial potential energy of the system and final potential energy. Then we will be able to find out what is the change in potential energy. Potential energy of the Q1 and Q2. Okay, what is it? 1 by 4 pi epsilon naught Q1 Q2 by what is the distance between them? 0.3 in terms of the SI system of unit, plus potential energy of Q1 Q3. Q1 is here, Q3 is here. Distance between them is what? 0.4 meter. So 1 by 4 pi epsilon naught Q1 Q3 by 0.4. What about the potential energy of the Q3 Q2? 1 by 4 pi epsilon naught Q3 Q2 by, what is separation between them? 0.5. So this is about the total initial potential energy of the combination. Now we look at the final arrangement. So final arrangement is what? Only the charge C place is displaced. Charge C, charge which is at C, right, which is Q3, is brought from point C to point D. So we will see what is going to happen as a result of it. So now we have charge Q1 as it is at point A, Q2 is as it is at point B, and Q3 is coming to the point D. So this gap is 30 centimeters. This gap is what? 10 centimeters. In terms of SI unit, this is what? 0.3 meter, 0.1 meter. Now we'll have how many potential energy terms? Same 3 potential energy terms. One is Q1 and Q2. Other is Q1 and Q3. Q1 Q3 interaction. Then Q2 and Q3 interaction. These are the 3 terms. Now Q1 and Q2 means what? Look at it. Q1 and Q2, gap between them is 0.3. So 1 by 4 pi epsilon naught Q1 Q2 by 0.3. In fact, we can see this term is as it is. It is not changing between the initial and the final. Q1 Q3. Q1 and Q3. What is the gap between them? Total separation is 0.4 meter. So what is it? 1 by 4 pi epsilon naught Q1 Q3 by 0.4. In fact, we will see this value also. Though the charge is moving from C to D, the separation between A to C is what? 40 centimeters. Separation between A to D is also 40 centimeters. That is the reason why the potential energy term is not changing. The only thing that will be changing is what? The third term, which is potential energy for the Q2 and Q3. So look at this Q2 Q3. What is the gap? 0.1 meter. So potential energy term will be 1 by 4 pi epsilon naught Q2 Q3 by 0.1. So these 3 will be the potential energy terms. Now change in potential energy is what they are asking. Means we have to do what? The total final potential energy minus total initial potential energy. So we can see 2 of the terms are as it is same. Potential energy of the Q1 Q2 pair as well as potential energy of the Q1 Q3 pair. These 2 values are as it is same. So now what we need to do? These 3 terms will be the total final potential energy. This is the total initial. We can see we have to do what? Final minus initial. That's what is change in potential energy, right? Means what? This is the final. We have to subtract the initial one. So this will be cancelled. Same is coming. This also will be cancelled. So this will remain in the final. What is it? 1 by 4 pi epsilon naught Q2 Q3 by 0.1 minus 1 by 4 pi epsilon naught Q2 Q3 by 0.5. So we have a 0.1 in the denominator. It will be what? It's like, we can write it as what? 1 by 10. So 10 will go to the numerator. So 1 by 4 pi epsilon naught is anyway common. Take Q2 Q3 also common. 1 by 0.1 means 10. 1 by 0.5 means 2. So 10 minus 2 will be what? 8. So Q2 Q3 by 4 pi epsilon naught into 8. Now if you look at it, they are saying the change in potential energy is equal to Q3 by, look at the term that they are giving. They are saying, it is what? Q3 by 4 pi epsilon naught into K. Equate both of them. Q3 is cancelled. 4 pi epsilon cancelled. What we will have? K is equal to what? 8 times Q2. K will be equal to what? 8 times Q2. So what is the correct answer for this? Option C. What we are doing is we are simply writing down what are the potential energy terms involved initially and finally. Change in potential energy means what? Final minus initial. Next we have a question that has come in 2004. A bullet having mass 2 grams is having a charge of 2 microcoulombs. Micro means what? 10 power minus 6. 2 grams means what? 2 into, we can say, 10 power minus 3 kg in terms of the SI unit. Through what potential difference must it be accelerated starting from rest? Starting from rest, through how much potential difference it should be accelerated so that it acquires a speed of 10 meter per second. So you have a charged particle. If it is accelerated through a potential difference V, means this accelerating through a potential difference. This wording is generally used when the charged particle is going from high potential to low potential. So as a result, its potential energy will be decreasing. As a result, what is going to happen? Its potential energy will be decreasing. And the decrease in potential energy will result in the form of increase in kinetic energy. That is what we refer as the accelerating through a potential. Means it will be going through a region from high potential to low potential. So when it is having a potential drop or decrease of potential V, the potential energy loss will be equal to what? The charge Q times V. That is the potential energy loss, because if it is having a drop in potential of V, the corresponding gain in kinetic energy, because it is starting from rest, gain in kinetic energy means what? Half mv square. Here we should keep one thing in mind. This capital V is what? Potential, and this small v is the velocity. So look at it. We have to equate both of them. That's it, right? Whatever is the loss in the potential energy is resulting in the gain in kinetic energy. Means what? Half into mass of the object. What is the mass of the object? 2 into 10 power minus 3 into V square. Everything we are taking the SI system is equal to what? Q, charge. Charge is what? 2 into 10 power minus 6 into capital V. This is the voltage. So everything is in the SI system. So the potential difference value V will be coming in the volt. So look at this here. What is going to happen? 2 is cancelled. This is 10 power minus 1. Right hand side, what do we have? The 2 into 10 power minus 6 will come to the denominator. So 10 power minus 1 by 2 into 10 power minus 6. That is V. 10 power minus 6 will go to the numerator as 10 power 6. So 10 power 6 into 10 power minus 1 by 2. That is what V. So what do we have? 10 power 6 into 10 power minus 1 means 10 power 5. 10 power 5 by 2. 10 power 5 divided by 2. That is the V value. So this we can write as what? If we have 100 into 10 power 3 divided by 2, that will be what? So 10 power 5 can be written as what? 100 into 10 power 3. So 100 by 2 is what? 50. 10 power 3 kilo. So what is the potential difference through which it is accelerated? 50 kilovolt. Correct answer for this is option B. It's a straightforward question. Just we are equating the loss in the electrostatic potential energy to be equal to gain in the kinetic energy. Next we have a question 2004. It has come. It is based on the electric dipole. An electric dipole has a magnitude of its charge Q and its dipole moment is P. What is the charge magnitude? Q. Dipole moment value is P. It is placed in a uniform electric field E. If its dipole moment is along the direction of the field, means what? Here they are saying it is a uniform electric field. Let us say the electric field is like this, towards the right side. This is uniform electric field. How do we generally represent the uniform electric field? By parallel lines having equal separation. We can clearly see the dipole moment is aligned, or it is along the direction of the field. Means the dipole is kept like this. The arrangement we will call it as what? Parallel arrangement, or theta is equal to 0. Theta means angle between. Theta is what? The angle between dipole moment and E bar. Okay. the force on it and its potential energy respectively. See, when you have a dipole in uniform electric field, irrespective of how the dipole is placed, means in what orientation it is placed, always the net force acting on the dipole will be zero. This is independent of the orientation. Why? Because a dipole will have what? It will have a combination of two equal and opposite charges. Uniform electric field, right? Force acting on the negative charge will be what? Minus Q times E. Force acting on the positive charge will be what? Q times E. So if you are looking for what is the total force, means what is it? We have to add both of them, right? So total force on the dipole, irrespective of what is the orientation, total force will be always zero when it is kept in the uniform electric field. That is the case here. So first thing is what? Force is zero. By this itself we will be able to conclude the answer. Look at it. Force is given as zero in only one case, that is option C. Now what about the potential energy for the dipole, right, which is kept in a uniform electric field? The potential energy, what is the expression for the potential energy? It is minus PE cos theta or minus P dot E. When theta is equal to 0, that is the orientation given, right? Theta is equal to 0 means here we will get what? Cos 0, which is 1. So in this case the potential energy will be minus P into E, which will be the minimum energy that the dipole can ever have. Because as it moves away from this theta is equal to 0, theta is equal to 0, that's the reason why it is called as what? It is also called as what? Stable equilibrium. Because in theta is equal to 0 arrangement, the dipole will be having the potential energy to be what? Minimum. And the value will be what? Minus P into E. So the correct answer is what? Option C. Force will be 0 and potential energy will be minimum. Next we have a question. It has come in 2003 based on the capacitors. 3 capacitors each having a capacity 4 microfarad are to be connected in such a way that the effective capacitance is 6 microfarad. This can be achieved by, or this can be done by. So this kind of questions, right? Either we will go through the options, because 3 capacitors, imagine we have 3 capacitors. How we can arrange them? We can think about arranging them all in series. If we keep all of them in series, right, 1 by C equivalent is equal to what? 1 by 4 plus 1 by 4 plus 1 by 4, that is 3 by 4, means C equivalent is coming as what? Reciprocal, 4 by 3. But here the effective capacitance they are saying is what? 6 microfarad, means connecting all of them in series, that is not going to give us. If we connect all of them in parallel, means what? Parallel, C equivalent will be equal to what? C1 plus C2 plus C3. What is it? 12 microfarad. But here they are saying the effective capacitance is what? 6 microfarad. So this is also not correct. Then look at option C. Connecting 2 in series and 1 in parallel. So means what? We keep 2 of the capacitors in series, and to that particular branch the third is kept in parallel. Means here we have a 4, here we have a 4, and this is a 4. So let us give them some numbering: C1, C2, C3. C1 and C2 are in series, right? So we have to find the overall equivalent capacitance. Means first we have to simplify C1 and C2. That is what? From here there is a series arrangement, right? Means we are finding the equivalent of this C1 and C2. 1 by 4 plus 1 by 4, which is what? 2 by 4, that is 1 by 2, means C equivalent will be what? 2. So when we find equivalent of the C1 and C2 value, that is coming as what? 2. Now the 2 and 4 are like in parallel. Means what is the final equivalent capacitance? 2 and 4 parallel means 2 plus 4, that is going to be what? 6. So what is the correct arrangement that we need to be having? We should have 2 of them in series and 1 should be connected in parallel. So the right answer for this is what? Option C. We can check the other arrangement also. What is the other arrangement? Connecting 2 in parallel and 1 in series. Means what? We have to keep 2 of them in parallel and 1 should be in series. Means this is how it should be. So first we should have 2 of them in parallel. And then there will be a third one which is in series like this. So this is a 4, this is a 4 and this is a 4. Now again we can number them C1, C2, C3. Equivalent of the C1 and C2 is what? Both of them in parallel, right? Means what? Equivalent will be 8. Now it is like the 8 and 4 are in series. How do you get the overall equivalent? 1 by C equivalent is equal to 1 by 4 plus 1 by 8. What is this? This is 3 by 8. So C equivalent will be equal to what? 8 by 3. So you see that it is not equal to 6 microfarad. Okay. So the answer is what? Option C only. So for these kind of questions, right? What? Because it depends upon what kind of question they are framing. So we'll probably have to go and check with the assumptions that are given or the options that are given. Next we have a question based on the electric flux. This has come in the 2003. A charge Q is located at the center of a cube. Means think about a cube. Cube is what? It's an enclosed surface. The charge is kept symmetrically at the center. Charge Q we are keeping at the center. The electric flux through any phase for a cube, right? How many phases will be there? This side 1, 2, 3, 4, 1 below, 1 above. So 4 we can say sidewise or lateral phases and 2 phases where 1 above and 1 below. So totally we have 6 phases. But with respect to the charge at center, all 6 phases are what? Symmetrical. Means from this charge, if say for example through the phase 2, let us say some 100 field lines are leaving. Phase 5 also how many field lines will be leaving? 100. Phase 4 also 100. Phase 3 also 100. Like that. All are symmetric. Now as a result of it, right? Remember, flux through the enclosed surface. Flux through enclosed surface is what? Charge inside by epsilon naught. This is the Gauss law. Okay. But they are not asking what is the flux through the cube. They are asking flux through any phase. See, 6 phases are there, each are identical. Means what? The total flux through the cube will be equal to what? 6 times flux through each phase. Because all are identical, right? So 6 times, if you take flux through each phase as 5 phase, then 6 times of this will be the total flux through enclosed surface. This is equal to Q by epsilon naught, which means flux through a single phase will be equal to what? 1 by 6 epsilon naught into Q. Basically the 6 will go to the denominator, that's it. But if you look at these options, right, we don't seem to be having this option as it is. Why? Because if you carefully take a look at it, right, look at option B, the 4 pi and 4 pi can be cancelled. Then what is it equal to? Numerator we have Q. Denominator is what? 6 epsilon naught. So what is the correct answer for this? Option B. The moment we are not able to see this answer, don't jump to the conclusion that there is something wrong. We may have to sometimes write. It is possible that we may have to do some simplification with regard to the given answers itself. Next we have a question that has come in the year 2002. Identical charges minus Q are placed at each corner of the cube side B, then the electrostatic potential energy of the charge plus Q, which is placed at the center of the cube. Same cube concept. We have a cube. Cube will have how many corners? There will be 8 corners. Identical charges minus Q. Each corner we are keeping minus Q. All the 8 corners minus Q, minus Q, minus Q and minus Q. Then a charge plus Q is placed at the center. Charge plus Q is placed at the center. The electrostatic potential energy of the charge plus Q we have to find. We have to find what is the electrostatic potential energy of the charge plus Q. Now the charge plus Q at the center of the cube will interact with all the 8 charges. So the plus Q will interact with each of the charges at corners. And in a cube, right, the side length of the cube is given as B. For a cube, the diagonal on the face, means you take any face, the diagonal will be, so this is B, means this is also B. You see a right angle triangle. Pythagoras theorem says hypotenuse is what? Root of base square plus height square, means the face diagonal will be root 2 times B. For any cube, these are the things that you will be referring to in chemistry solid state chapter also. For any cube, face diagonal will be what? Root 2 times B. B is what? The edge length. And body diagonal. So body diagonal means from one corner to the opposite side corner, that will pass through the center of the cube. So body diagonal means what? Maybe we'll just erase this and then redraw the diagram. Body diagonal means what? The diagonal that will pass from one corner to other corner of the cube through the center. That is what we call as the body diagonal. So if you have a cube like this, body diagonal will be from one corner to exactly opposite corner. This is what we call as body diagonal. This will pass through center. And body diagonal value, right, how do we get it is, we take the face diagonal and we will be able to create already we have said the face diagonal value will be what? Root 2 times A. And you look at this edge, not root 2 times A, root 2 times B. Here we are taking the edge length as B. This is a B. You see, this is the right angle triangle. This is our body diagonal. So the face diagonal root 2B and edge B, they are like the adjacent side and the height. Hypotenuse is the body diagonal. So body diagonal will be equal to root of B square plus root 2B the square. That will be totally root 3B. That is what is the body diagonal. So distance from center to the any corner will be half the body diagonal, because symmetrical, right? Center is at the symmetrical point, means from the center of the cube to any corner the distance will be what? root 3 b by 2, that is the distance from center to any corner of the cube. Now charge arrangement is given. What is charge arrangement? We have all 8 corners, charges minus q are kept. Center we have plus q. We need to find what is the potential energy of the charge kept at the center, which is the plus q. So if you look at the charge kept at the center, let us look at the interaction between the charge at the center and one of the corner charges. Potential energy for this will be what? 1 by 4 pi epsilon naught q into minus q divided by distance. Distance is what? Root 3 b by 2. So 2 ones are 2 twos are. So what is it? Minus q square by 2 pi epsilon naught into root 3b. Now this charge will engage in totally 8 such potential energy interactions, because we have 8 minus q charges, one at each corner. So the charge at the center will engage in 8 such interactions. So the total potential energy of the charge at the center will be what? 8 times of this value. So 8 times of minus q square by 2 pi epsilon naught into root 3b. So we'll see here what will get cancelled. We can say 2 ones are 2 fours are. So what we'll have is minus 4q square by root 3 pi epsilon naught into b. What is the correct answer? It is option C. Minus 4q square by root 3 pi epsilon naught into b. So all we are doing is, in this we have spent some time to calculate what is the body diagonal of the cube. But if based on your understanding of the solid state chapter in chemistry, if you are familiar with these length measurements, right, you will be able to straight away proceed with the calculation step, because we need to know what is the distance from corner to the center in a cube. That is what? Root 3b by 2. Root 3b will be the body diagonal, and half of that will be the distance from corner to center. So that way we will be able to find out the distance from corner to center. Once we get it, the arrangement is symmetrical. So potential energy for one interaction is what? The interaction between a charge at the center and peripheral minus q is what? This much. We have 8 such interactions, right? So total energy will be what? 8 times of that. So we'll get option C. Next we have a question that has come in the year 2002. A capacitor having capacitance C1 charged up to voltage V, and then connected to an uncharged capacitor of capacitance C2. Means first this one is charged. So what will be the charge on this? Charge on this will be equal to what? C1 into V, because it is charged by using a voltage V, right? So after this, it is connected across a capacitor C2. This is uncharged. C1 is basically charged and the other one is what? Uncharged. Now we connect. The final potential difference across each of them means once we connect the two capacitors, what is going to happen is there will be charge transfer till the potential on each of them will become equal. Let us say that final potential is some V dash. The final potential is V dash. Now what will be the final charge on the capacitor C1? C1 into V dash. What is the final charge on the capacitor C2? Because that also will have the same potential finally, right? C2 into V dash. This total charge is nothing but the charge we have originally. That charge is what is getting redistributed. What is the charge we have originally? C1 into V. This is the original charge. So final charge on the capacitor 1 plus capacitor 2 is equal to what? The original charge, which is the charge on the capacitor 1. Now from here, look at it, left hand side, what do we have? C1 plus C2 into V dash can be common out. So from here, what is V dash? C1 V by C1 plus C2. That's it. What is the answer for this? It is option B. So when you connect the charged capacitor across the uncharged one, what is happening? Charge transfer happens till both the capacitors will get the same potential. Some charge is being given to a conductor, then its potential is. So if you have a conductor can have any shape. Generally we will consider the metallic objects to be the conductors. It may be irregular shape like this, or it may be a regular shape like a conducting sphere. It can be any shape. Now we have to comment on the potential. Look at this. Option A is saying potential is maximum at the surface. Option B is saying potential is maximum at the center. Option C is saying potential remains same throughout the conductor. Option D is saying is maximum somewhere between the surface and the center. Now this conducting sphere example, right, is something that we would have analyzed during our theory class or the preparation. When we give charge to this conducting sphere, we'll analyze this with an example so that we will have some familiarity. We know that not only for this conducting sphere, any conductor, when we give charge means charge will be residing on the outer surface. Inside the conductor, electric field will be 0. Whether it is a spherical shaped conductor or irregular shape, any shaped conductor, inside the electric field is what? 0. Which means when we move from the surface into the conductor, in this region when we are moving there is no electric field, means potential difference will be 0. In a region where there is no electric field, potential difference will be what? 0, which means from the surface we begin, means as we get into the conductor, wherever we go, potential difference is what? 0, which means the potential everywhere inside the conductor, the potential everywhere inside the conductor is same, and is same as what? Is same as the potential on the surface. It is not only same, it is same as potential on the surface. So look at it, what is the correct answer? The potential, right, will remain same throughout the conductor. This is not only for the spherical conductor but any random shaped conductor also this is going to be true. So this is about this part video, and we'll see in the next part.